Hi everyone, we are going to go through the solutions to the assigned questions for 7.5 here. The normal approximation to discrete random variables, mainly the binomial and hypergeometric distributions. Let's start with question 3. 2 dice are rolled, a double is considered a win, and anything else is a loss. What is the minimum number of rolls that should be made to model this situation using a normal distribution? Now remember, in order for that to be the case, NP and NQ both have to be greater than 5. Now, what is P here? Okay, double is considered a win, so remember, the probability of getting a double when rolling 2 dice is 6 over 36, right? Which we can simplify to 1 over 6. A failure is not getting double, so that's just 1 minus 6 over 36. That's 30 over 36, which we can simplify to 5 over 6. So we want n times 1 over 6 to be greater than 5, and n times 5 over 6 to be greater than 5. Now, whatever number we get for n here is definitely going to be make this criteria work too, right? Because here we have 5 over 6, which is a bigger number. So we just have to focus on this right here. All right. So n over 6 is greater than 5. And if you multiply both sides by 6, we need to have n to be greater than 30. Okay, and what's the next number greater than 30? It is 31, right? So we need a minimum of 31 rolls. Okay, that is the requirement in order for this situation to be accurately modeled by a normal distribution. Question 4. A barrel at the pro shop contains 30 white golf balls, 20 yellow golf balls, and 10 orange golf balls. A contest requires a contestant to blindly select several balls without replacement. The prize depends on the number of orange golf balls obtained. What's the maximum number of balls that could be selected to model the contest using a normal approximation? Okay, we're taking balls out without replacement. This means we have a hypergeometric distribution here. Okay, and the requirement for this to be accurately modeled by a normal distribution is that the sample size needs to be less than 1/10 of the population. NP, capital NP here means the population. So n needs to be less than 1/10 of all the golf balls, right? 30 plus 20 plus 10, which means n needs to be less than 60 over 10, which is 6. So what's the next number below 6? It is 5, right? So the maximum, it would be 5 golf balls that you can take out. 5 cards are dealt from a deck of 52. The number of cards is counted. So you can see right here, remember, being dealt a hand of cards, that's a hypergeometric distribution. Okay, because the cards are not replaced. Is it reasonable to model this distribution with a normal approximation? So n is equal to 5. The number of cards is 52. Is n less than 1/10 of 52, right? Is 5 less than 5.2? Yes, it is. Okay, so it's going to give us a fairly decent approximation. What mean should you use? Remember, the mean is calculated by n times p. Okay, so 5 times the probability of a success. Okay, there are 13 out of 52 cards that are hearts, so that's actually 1 over 4, so 5 over 4, which is 1.25. All right, so that's our mean. What standard deviation should you use? The standard deviation, remember, is the square root of npq times np over n minus 1. So np minus n over np minus 1. So that is equal to 5 times 13 over 52 times 39 over 52 times 52 minus 5 all over 52 minus 1. If you were to simplify that, we're going to get about 0.93. Six, a special high occupancy vehicle lane along a highway is reserved for cars carrying 2 or more people. Police indicate that 8% of the cars in the high occupancy vehicle lane are occupied by fewer than 2 people. A random police check observed 100 cars. Okay, so this is a binomial distribution, right? Even though there are a limited number of cars, there are a very, very, very large number of cars. So we can just use the binomial distribution. So let's state our parameters first. P is equal to 0.08, right? 8% of the cars don't have enough people, okay? And that's what's considered success here. Q 0.92, which is just 1 minus P. We have a sample of 100, and we're trying to see the probability of getting 10 that have fewer than 2 people. Okay, so use the binomial distribution. Okay, if you recall the formula, and choose x times p to the power of x times q to the power of n minus x, right? That's our formula. So 100 choose 10 times 0.08 to the power of 10 times 0.92 to the power of 90. That is approximately 0.0578. So you have about a 5.78% chance of getting exactly 10 people, with exactly 10 cars with just one person. Okay, now let's try. Okay, sorry. Now let's try to use. The normal approximation to determine the probability that exactly 10 of the cars contain one person. So our mean is NP, okay, which is 0.08 times 100, okay, which is 8. And our standard deviation is the square root of NPQ, which is the square root of 100 times 0.08 times 0.92. That is going to give us approximately 2.71. Okay, now next up we have to use next up we have to use get the z-scores. Okay, so for exactly 10 we're gonna get 9.5, okay, and we're going to get 10.5, the z-scores for that. Okay, so let's call the first one z1. 9.5 minus 8 all over 2.71 is equal to approximately 0.55. The second z-score, 10.5 minus 8 over 2.71, is equal to approximately 0.92. So if we want to get the probability of that, we have to look up our z-score table. Okay, subtract those values that we find on the z-score. You should see 0.8212 minus 0.7088. That is equal to 0.1124. Okay, now so let's compare the probabilities. All right, I just noticed I made a mistake. My apologies. For A, this should not have been 0.00578. Did something wrong with my calculator. It is actually equal to 0.1024. Okay, so it is quite close. Okay, we have 0.1024 and 0.1124. So there's a difference of 1%, which is not insignificant, but still it's quite close. Okay, so our normal approximation did work. We can be pretty certain about that. Okay, so for C, we can just say that the two values are very close. Okay, let's look at question 8 now. A card is drawn randomly from a deck and then replaced. The deck is shuffled, 10 trials are carried out. Okay, so we know that this follows a binomial distribution, right? Because we have replacement. Okay, so A says use the binomial distribution to determine that the probability that there are exactly 5 diamonds and 10 trowels. All right, so once again, let's state the parameters. N is 52, there are 52 cards. Okay, the number of diamonds we are looking for is 5. The probability of success is 13 over 52, which is 1 over 4. The probability of failure is 1 minus 1 over 4, which is 3 over 4. And we can just plug the numbers into the formula. Okay. Sorry, my mistake. N is not 52. We are taking out 10 cards, so 10 trowels. All right, so plugging in the numbers in, we should get 10 choose 5 times 1 over 4 to the power of 5 times 3 over 4 to the power of 5, which is going to give me about 0.0584, about a 5.84% chance. Okay, B, could you reasonably model this distribution using a normal approximation? NP is 10 times 1 over 4, which is 2.5. So the answer is no. Okay, but even though that's the case, we're still going to get a very close answer for this question at least. But usually, or a lot of times, if it doesn't meet the criteria, we're not going to get a very good estimate. Okay. C. Okay, calculate the mean and standard deviation. The mean, we already calculated, NP is 2.5. The standard deviation is the square root of 10 times 1 over 4 times 3 over 4, which is approximately 1.37. Okay, so exactly 5 diamonds, we're going to use 5.5 and 4.5 for our x values. So let's start with 4.5. That's approximately 1.46. That's our z-score. And for 5.5, we are going to get approximately 2.19. Okay, now if we look up our z-score table to calculate this probability, we are going to get 0.9857 minus 0.9279, which is going to be 0.0578. Okay, so that's where the 0.0578 came from. Okay, so we can see that they're still quite close, even though we didn't meet our NP and NQ criteria. They are still very close. Okay, so that is our answer for E. They're very close in this case. They're close by. There's only a 0.6% difference there. Okay, so we got a good estimate. 10. An insurance company knows that 12% of the homeowners in a town of 900 are customers. The marketing department calls 50 homes at random. Was there probably 10 or more of these are already customers? All right, so they're probably at 10 or more. Okay, so let's set our criteria first. We have 900 people. Sorry, that's NP. Okay, this is a hypergeometric distribution, right? Because when I call one person, I don't call them again. So the probabilities change. Our sample is 50, right? It calls 50 homes. Okay, 900 people. The probability of success is 0.12. Okay. All right, now when we plug the numbers in, our mean is going to be 50 times 0.12, which is 6. Our standard deviation is 50 times 0.12 times 0.88 times 900 minus 50 over 900 minus 1. That's going to be approximately 2.23. Now, I want to find the probability of x being greater than 10, right? Greater than or equal to 10. So we start at 9.5 because we want to include 10. All right, so our z-score is 9.5 minus 6 all over 2.23. That's around 1.57. Okay, so we want to find the probability of a z-score greater than 1.57. So 1 minus, when you look up the z-score table for 1.57, we're going to get 0.9418, which is going to give us around 0.0582. All right, so there's about a 5.82% chance that we'll have 10 or more that are already customers. Okay. So what method do you choose to solve this problem? Now, in this case, we use the normal approximation. Now, why is that? It is faster, okay? To get the exact probability, we need the probability of, if we use the hypergeometric distribution formula, we have to do probability of x equals 10 plus the probability of x equals 11, and we have to keep on going until we get the probability of x equals 50, basically, okay? And that takes a long time. So this is a clear example of how the normal approximation helps us, okay? We can get a very good estimate very quickly, okay? Instead of calculating the exact probability for 10 people, 11, 12, 13, up to 50, and then adding them all up, okay? All right, that concludes the answers for 7.5.